Congratulations, you've successfully trained your first neural network. We are now going to plot our data set along with a precise decision boundary that will separate our categorical results. The equation for this decisive boundary layer is obtained directly from the neural network after it goes through the entire training procedure that we saw earlier. So in order to display our model, we must first start by defining a function, def, called plot decision boundary. Feel free to call it whatever you want. And now this function is going to accept three arguments: the array of data, the labels, and the model. The first argument x refers to the data that we created earlier in the code, the ones in the bottom and the ones on top. The second argument y refers to the matrix, which contained labels for our data set, 1 for the bottom region, 0 for the top region. And finally, the last argument model refers to the sequential model we created earlier containing all of our neural network data. Before proceeding any further, let's actually just call this function in our separate cell and get a head start. So we'll just copy and paste that, plot decision boundary, with the arguments x, y, and model. So this function is going to take the arguments that we're passing into it, and it's going to manipulate them accordingly to return a contour plot of the decision boundary, the boundary that's separating our data. We're going to have a contour plot of it. So what we want to do is actually have a grid that properly spans all of our data. This process begins by defining a span of the x and y coordinates within our datasets. The x span is going to be defined as 50 equally spaced points, np.linspace, between the absolute minimum, min, the minimum value in the array x. We'll index every single row in our matrix with the colon in the first column at index 0. I've already explained in the previous section how all the horizontal coordinates are in the first column of our array, and we've already dealt with this code. Ultimately, what this will do is it will give us the minimum horizontal value in the first column, the point whose value is furthest to the left of the coordinate space. And we also want the absolute maximum, max, and we still want to index all the x coordinates in the first column of our array. We'll index all the rows with a colon in the first column of index 0, and ultimately this gives us the maximum horizontal value, the point that's furthest to the right of our graph. If we actually go ahead and print this, print x span, we obtain an array with 50 equally spaced points from our minimum horizontal coordinate at point 2.0 to the maximum coordinate 18.392, and all these points are just equally spaced intervals between our minimum horizontal coordinate and the maximum one. Similarly, we're going to define the y-span also as 50 equally spaced points with np.linspace between the absolute minimum vertical coordinate of our data set, the point that's furthest down. We want the min value that's in the array x. We'll index all the rows, but we want all the rows in the second column at index 1, since we've already seen in the previous section how all the vertical coordinates are in the second column of our array at index 1. And to complete our linspace, we're going to grab the maximum vertical coordinate value in our data sets. Max at x, we're indexing all the rows at column 1. Now printing y-span, we obtain the vertical coordinate of the point that's furthest down and the vertical coordinate of the point that's furthest up, and equally spaced intervals in between. You'll see why we're doing this in just a bit. I know we're just doing very simple NumPy, but this is all going to come full circle in just a moment. And to actually complete this, what we're going to do is add some tolerance to our x and y spans by subtracting 1 from the minimum values and by adding 1 to the maximum values. We'll do that for both the horizontal and the vertical. This tolerance will simply create a more visually appealing and a more spacious grid for our data. All we're doing is simply spacing out our range. That way, the line goes 1 unit further to the left at coordinate 1 and 1 unit further to the right at coordinate 19. And it does the same thing vertically. If you were to print the y-span, our range goes 1 unit further down at negative 0.08 and 1 unit further up at 18.5. Okay, nothing interesting so far. All we've done is created two one-dimensional arrays, x-span and y-span, where one array spans the entire horizontal range of our data and the other array spans the entire vertical range. We now define the variables xx and yy. The xx and yy variables will both hold a square two-dimensional array that is obtained from the numpy.meshGrid function. Since we didn't cover mesh grids in the NumPy crash course, I guess there's no harm in explaining it now. If you're already familiar with meshGrid, feel free to skip the next 2 or 3 minutes of this video. But essentially what this function does is it allows us to return coordinate matrices from the input of the coordinate vectors. I'll explain what I just said momentarily, but for now, we'll simply place our previously obtained coordinate span vectors as arguments into this function, xspan and y-span. What this function is going to do, it's going to take the xspan vector, which contains 50 elements, and it returns a two-dimensional 50 by 50 matrix. The newly added rows are simply repeated copies of the original row in the xspan vector. This new matrix is then returned to the xx variable. Similarly, the function takes the y-span vector as a second argument, and from the y-span, which is what you're seeing right now, what it's going to do is convert this to a 50 by 50 matrix as well. But this time, the newly added columns are repeated copies of the original column in the y-span vector. This new matrix is then returned to the yy variable. Perfect. To better visualize what I just said, let's actually have a linspace of 3 elements. The default is 50. We will put a linspace of 3 in each one. We're going to print our xx variable. We'll print the yy variable as well. Alright, so first we have our xx, which is a 3 by 3 array whose rows are repeated copies of the original row. And yy is a 3 by 3 array whose columns are repeated copies of the original column. Why did we just do that? Well, that will make sense in just a bit. Because if you imagine a 3 by 3 grid, for every y coordinate, there are 3 corresponding x coordinates. The same thing would occur with a 50 by 50 grid, which is what we're actually going to work with. So let's put this back to 50 by 50. And the end goal, what we're going to do is from these two arrays, we'll define a 50 by 50 grid, which spans the entire horizontal and vertical range of our data. So using these newly created matrices xx and yy, we can now create a Cartesian grid that covers our data set. However, if I were to actually reprint xx or yy, whichever one, notice this is a two-dimensional array. We need to actually flatten both xx and yy into one-dimensional arrays. You'll see why in a bit. We will store our flattened arrays as xx and yy underscore respectively, and we'll do that with a ravel. Remember ravel? It wasn't in the crash course for nothing. Let's use it. This flattening is going to be done with xx.ravel and yy.ravel. If we print both xx underscore and yy underscore, clearly both arrays are now one-dimensional. Notice the single brackets. And now the reason why we did this is going back to the example of our 3 by 3 grid. Let's put this back as a 3 by 3. If we were to actually concatenate these arrays, Notice how for every single y coordinate, there are 3 corresponding x coordinates, which, if you think about it, defines a grid. The same thing would occur with our 50 by 50 grid. For every y coordinate, we're going to have 50 x coordinates. So, to define a grid, we have to concatenate these arrays in a column-wise arrangement. We'll do that by setting grid is equal to np.c underscore, a handy function that we can use to concatenate these flattened arrays column-wise. We just need to pass them in, xx and yy. Let's output the grid. Let's print the grid. And now notice how for every single y coordinate, there are 3 corresponding x coordinates, which defines the grid itself. And the same thing would occur with a 50 by 50 grid. So we'll go ahead and make this a 50 by 50. This was just for you to visualize it better. And you know what? The default is 50, so we don't actually need to specify. Alright, now we have a 50 by 50 grid that spans across our entire dataset. Enough of NumPy. Now we can use the model.predict function with grid as the sole argument. By feeding the entire grid array into the model.predict function, the trained model tests all the points inside of our 50 by 50 grid. It's going to test all of them and returns an array of predictions. These predictions indicate the probability of any given point being labeled as 1, the probability of a point being in the positive region. Obviously, these points will have low probabilities close to 0. These points will have high probabilities close to 1. Notice how easy it is to make predictions. Instead of having to specify the sigmoid of a linear combination of every single point like we did in pure Pythonic code in the last section, this function takes care of all of our dirty work. One of the many reasons that makes Keras so user-friendly. So what we're going to do is we will store this array of predictions under the name predfunc. You can call it whatever you want. I find this to be a suitable name. And what we want to do is actually reshape this array to have the same dimensions as xx or yy, whichever one. This simply ensures that the prediction results are compatible with the appropriate coordinate counterparts of our grid. So we'll define an array z and set it equal to a reshaped predfunc. We'll reshape our predictions, predfunc.reshape, and we will give it the same shape as one of our grid spans. So we have a 50 by 50 array of predictions which match the coordinates of every single point in our grid. By doing this, we're allowing the shape of our prediction data to be consistent with the 50 by 50 shape of our graph, such that every single coordinate in the graph would have its corresponding prediction. So now our prediction results are linked to their appropriate coordinate counterparts. The final role of our defined plot decision boundary function is to create a contour plot of our predicted results using the plt.contour function with the xx, yy, and z arguments. We'll actually use contourf for a 2D contour plot. Let's run all of our cells. The arrays xx and yy represent the x and y values of each coordinate in our grid respectively. As mentioned earlier, the array z contains the magnitude of the probability at each corresponding coordinate. The more the point is in the positive region, the higher its probability is going to be. And now feeding this array as the final argument allows the plot.contour function to correlate each specific coordinate with its respective prediction probability. And based on that, the function then plots distinct contour zones, each of which represents a distinct probability level. This will be explained in further detail after we plot our points. So just be patient for now. Alright, now we will also plot our data set to get a better visual understanding of how the decision boundary separates our labeled data. As seen earlier, our data set can be plotted using plt.scatter, which we're just going to copy. Let's not reinvent the wheel. We'll copy this right over here along with our contour plots. And running this, we can finally see our decision boundary plotted side by side with our data set to get a better visualization of our model. And as you can see, our decision boundary contour plot, these contours right here, very effectively separate our data points into the appropriate labels of 1 here and 0 here. As mentioned earlier, the plot.contour function simply plots distinct contour zones. Each one of these contour zones represents an increased threshold of probability. This blue zone that I'm pointing to right now represents the lowest probability of a point being labeled as 0. This means that any point inside of this zone and beyond most likely has a predicted label approaching 0. The probability that a point is labeled as 1 increases as you go from the absolute blue zone to this yellow zone over here. Any point inside this yellow zone is most likely going to have a label approaching 1, and the further we go into the yellow zone, the more we're in the positive region, the more we approach a label of 1. So we have our model that perfectly classifies our data into distinct classes. I wouldn't say perfect, more like 97% accuracy, which is pretty good. What we'll do now is actually take this one step further and learn how to plot and obtain a prediction for a single chosen point. We've talked about this a lot in theory, but for once, let's actually implement it. So what we'll do actually is replot our data and decision boundary just as we did before in this new cell. And now we will decide the coordinates for our test points. We will define a point with horizontal coordinates, let's say of 7.5 and a vertical coordinate of 5. We will define a point that's right over here. You know what? Instead of going any further, I just want to emphasize that we trained a neural network based on previously labeled data to come up with the perfect model that classifies them, or the most optimal model. And now, from our model, we can make predictions of newly inputted data which don't have a label. So let's actually declare the point whose label we want to predict based on our model. X is equal to 7.5 and y is equal to 5. And next we create an array called point is equal to numpy.array. And this will simply contain our x and y coordinates. And now we can obtain a prediction value by feeding our points, our coordinates, into model.predict point. And we will set prediction equal to model.predict, equal to the return value of our prediction. And what we'll do actually is plot this point alongside our data by using plt.plot, and the first and second argument require lists of x and y coordinates, but we're only going to plot a single point with the x and y coordinates that we specified, x and y, and we will set a marker equal to O. That way it shows up as a circle, an O. The marker size will be 10. That's pretty self-explanatory, just the size of the marker, and the color is red. Any color you want, it's up to you. Okay, let's also print the prediction. Prediction is the prediction itself that we obtained from model.predict. All right, let us run this. Clearly the marked point is visible among the data points that are labeled as 1, and as expected, the prediction value returned for this point is very close to 1, indicating a very high probability that this point is labeled 1. It was indeed correctly classified by our model. I hope you guys enjoyed this lesson. I will see you in the next one.